Hello. So I'm back with another video in the series of building GPT-2, where we sequentially take small steps towards building a GPT-2 kind of model. And in the last video, we were building a multi-layer perceptron for next character prediction in our names dataset. So we have to generate names by taking in 3 characters, which was our block size, 3 characters as input, and it would have to output the 4th character. We built our data. We initialized the parameters. It was a uh, 2-layer perceptron. Our model, as of now, the last model that I trained had 181, 18,167 parameters, and I trained it for 200,000 iterations with varying learning rate, 0.1 till 50,000 iteration, and then 0.01. So I reached a lowest training loss of, or lowest dev loss of 2.163, which is better than our first 2 approaches of found-based method and the simple neural network, 1-layer neural network. And I tried to generate it using this learned model. So these were the names being generated by name Kashid Novathan, Kahim, Nivad, Izamairo. So they do sound like a little bit like the names, I think. But yeah. Now, if what I want to talk about, there are a few uh, uh, things about this network that we have trained that we can improve and which would be of great help going forward, because we are going to increase the complexity of these networks, particularly the forward pass. So these things that I'm going to discuss would be helpful in the further videos in future. So if you see at iteration 0, our loss evaluated was mini batch loss was 30.8, which is very high as compared to if you say that our loss should be nothing but 1 by 27 probability dot log and negative. Or maybe dot once 1 by 27 into 1 by 27 dot log. Okay, so ideally we would expect a loss of this range 3.29 initial loss, starting when, let's say, if a network is initialized from random numbers, it should not go very much above this, because this is something that we have calculated with the uniform distribution probabilities. But whereas if you see initially our loss starts at 30.8, which is way high. So we should figure out or investigate what is happening here. To do so, what we can do is reinitialize our network. And let's say after loss is calculated, let's put a break statement here. What I want to do is basically at this loss, the latest impact that the logits have is the latest impact, and the thing that is impacting on loss directly is logit. So we can see how the logits look like at this stage. So we have trained it for one iteration. So logits, we are expecting it to be of shape batch size by 27. Let's see if it is so. Yeah, 64 is our batch size 27. Okay, now let's print logits, what's going on in here. Okay, so you see that there are a lot of numbers you'll see of very high magnitude, 25, 7, 10, 8, 22, 11, -11, so on. Whereas by general norms of training neural network, it is believed that at each layer, after each layers, the outputs of a layer um, should look like Gaussian distribution. So basically, they should be centered at mean of 0 and having a standard deviation around 1. But this looks very spread out. The values are very high. We can see. So if we want to see what is happening here, what we can do is let me import matplotlib. Let's try to print plot a histogram of the logits. T.hist. We want logits to be plotted, but logits you see is of shape this batch size by 27. For plotting as histogram, we want everything as a vector of values, everything. So logits we'll view it as -1. So it would just become a single vector. Or if you plot this. Okay, so we had to convert this PyTorch tensor to list, numpy list, to use PLT function. I plotted with 50 mens. You see that there are a lot of very high magnitude values in the logits. So basically, this is what the issue is right now, because this means that logit, the higher value of logit basically means is that the network is very confident while predicting wrong predictions, while making wrong predictions. So that's why is increasing the loss to a high number. And so ideally we want these logits, or in general any output of any layers in a neural network, to be kind of unit Gaussian. So to do that, you can see that it is H matrix multiplied with W2 plus B2. That's how logits is calculated. So if we control initialization of W2 and B2 to a smaller, even further smaller values, we scale these down, maybe logits can come down further. Uh, Let me show this with an example. Let's say we take example of four logits of length 4. So this would be a normally distributed number. Right? It will be within the normally distributed range. So from this, if we derive probabilities, you can see that it's like this with softmax. Now, if we calculate loss minus probs, let's say for a particular example, our correct target class was 2. So probs of 2 dot log. This should be the loss. So you see the loss is well within the range, because the torch.randn is giving a unit Gaussian distribution of the logits. Now, if we multiply this with a larger number, randomly the values get large here, so our loss will start getting to higher values. It can be very low, it can be very large as well. So that's a risk we can run into. Therefore, to handle the Okay. So basically, to control the logits here, we can do some manipulations with initialization W2 and B2. If we scale these down, W2 and B2, let's say if we take these down to 0, and W2, let's say we scale them down by 10, so multiply it with 0.1. If we do so, what happens to logits? Let's take a look. Now you see the values have reduced from -4 till 4. Earlier it was going to from -40 till 40. So we were able to reduce them to a certain range, and in that case, how much is the loss coming out? It's 4.09. So it's much better now. No matter what we do now, we should have, see, 4.42. So we were able to control the logits using this scaling of the W2 and B2. Now another issue that exists here is the saturation of tan H. If we look at any point at a starting point, basically, if we look at the H pre-act, which is pre-activation layer outputs after doing this linear combination, embedding matrix multiplied with W1 and B1. So let's take a look at what is going on in here. H pre-act, we expect this shape to be 12 by 112, or others say batch size by 100, or maybe 200 now, because our hidden layer has increased. What is the shape? Yeah, 64 by 200. Okay. So now H pre-act. So you see the values are again of very high magnitude happening here. -12, 6, 6. So if you look at the uh, tan H plot of tan H, how it looks like, it is a squashing function of numbers between a range -1 to 1. But the saturated regions where the tan H outputs only 1 for very large numbers or -1 for very small numbers, that is called, you can call it them as saturated region. And for these very large values going into tan H will give output of just 1 or -1. And what happens when these are the outputs is, um, so when gradients are calculated, when backpropagation is done through the Stanich neuron, it will, when uh, the outputs of Stanich is 1 or -1, it will just zero down the gradient. So there won't be any loss passing through that particular Stanich neuron. Whereas only in the area where it is active, where it is like a curve, in that particular area, when the tan H is outputting any numbers, the the formula of the gradients of tan H will allow the gradients to pass through tan H. I'll quickly show what is the formula look like. Tan H. Right, so let me take a screenshot rather. So this is what tan H function is. And if you take a derivative of 10h with respect to z, with respect to the input, so it would be nothing but 1 minus a square. A is the output of 10h. So if the output is 1 or minus 1, this entire thing will become just 0. So with the chain rule, there won't be any gradients passing through backwards from that particular 10h neuron. Whereas if this number is between 0 and 1, there would be some gradients passing through. Ideally would be if this number is 0, that means when the input of tan h is 0, so entire gradient, whatever comes through this tan h neuron, can pass through backwards through the previous neuron. But yeah, so ideally that's why we ideally want the output of these activations to be of uniform Gaussian nature, so that they are numbers between 0 and 1, and they can allow gradients to pass through each of the neurons. So here, if you see, here basically the numbers are pretty huge. Now, if we just for namesake dodge.10, we print this, I'm expecting that many values would be like 1 or minus 1. Yeah, see. So with 6 as input, 1 is output, minus 6 as input, 1 is output. You can see a lot of ones and minus ones. Let's try to plot this. Or rather, we can just plot h. Yeah, it would be the same thing. Instead of doing this, we can just plot h dot view minus 1 to list bins 50. Okay. So if you see this histogram, most of the values you'll see occurring in this saturated parts where they are near minus 1 or 1. So this is what is very wrong happening with the network. And if you have a very deep network, these things cumulatively, they will just destroy your training optimization steps. So basically what we want is 10H outputs to be uniformly Gaussian in this nature, not mostly occurring in the saturated parts. So to do that, as we saw, H preact is getting really high values. So if we can control H preact, or we can initialize W1s and B1s in a way that H preact is itself is that H preact happening after calculation is not getting out of hands. It stays unit Gaussian or of small ranges. It could be good for us. So let's say we multiply this with 0.01, 0.01, and multiply this with 0.1. W1 and B1 as well. So let's see what happens. So loss further goes down. So that means scaling down W1 and W2 also further reduces the loss, initial loss. And how does our H preact look now? So right now, after previous case, we see that we had huge numbers. Now, cool. So yeah, the numbers came down to the very small range. To confirm that, we can look at this plot of H. All right, so it has become kind of a uniform distribution, or maybe some kind of Gaussian distribution. But yeah, most of the values are not going towards minus 1 or 1. Most of values are lying in the range in between in the active part of 10H. So this is how we can control this thing as well. Uh, so I think with this, we can run a training of the model with these changes. So basically, let me remove this break statement and 20,000. All right, let's run it and see what happens. Oh, sorry. My bad. I think I should remove this print statement from here. And now run this. Cool. So you see, initially iteration 0, the loss has reduced to 3.59, which is much closer to the range that we expected from this. Okay, I've deleted that cell, but we expected it in some range of 3 point something. So it is to our liking now. I'll let it run. Okay, so I let it run. We were able to reach to a loss of 1.77 with this. Let's take a look at the dev loss. We could reach 2.02, which is our best loss that we were able to achieve till now. And the generations look like Reiner, Nasia, JD, iPow, maybe. Yeah, it's getting better, I think. Okay, so another issue that can happen. So we have manually just scaled down all these initialization of weights and biases. But usually what happens is um, in today's date, most of the networks that we work with are pretty large. There are hundreds of layers, if not more, at least. So generally what happens, how it goes is mm, it would be very hard to scale down or put scaling to each of these layers manually, and we might not know what is the correct way to do for each of these layers with those all those complex networks now. So there's a better way to do this, which was introduced in a paper by Cunningham. The paper's name is mm, Delving Deep into Rectifiers. So before going to that paper, I'll quickly want to demo something for you. Uh, okay, let's say we have two tensors of shape 10 by 100 and x is dot rent and 8 by 10. So we have inputs of shape 8 samples of 10 features, and 10 features are going in input with the 8s, and the neurons are 100 neurons. So ideally both are initialized with rand, and so they are normally distributed variables. Let's say if we calculate x matrix multiply with w. So it would be interesting to see what would be the mean and standard deviation of our output. So mean is still around 0.01, but the standard deviation has increased to 3 now. So this shouldn't happen. Basically, when we are giving input, I don't mean this shouldn't happen. This happens because with this random numbers getting multiplied, the chances that the standard deviation goes high or stays in the range within the unit Gaussian range. So therefore, this is the problem that happens generally with these linear combination things that are going on here, h multiplied with w2 plus b2. So to do that, that's why we had to scale w1 to a point that could bring down the standard deviation of this, that could control the standard deviation of the matrix multiplication. Now, if let's say here, if we would have multiplied it with, uh, or rather divided it with, let's say 10 times 0.5 square root of 10, then just let's see how it impacts these numbers, right? So mean remains around 0. The standard deviation comes closer to 1. So what is happening here, why I chose this number is, let me go to the paper now. Okay, so this paper introduces, after its analysis and studies for ReLU linearity, that whenever we squash output from a layer with some kind of non-linearity, it does some kind of squashing. Therefore, there are some information getting lost. So uh, to manage loss of that information, we have to provide some gain to the, because distributions are getting squashed, right? Uh, to to compensate that loss in the distribution, we have to provide some gain to the uh, linear combinations that are happening, basically initialization of weights. And that is one part. And another part of this paper is we have to scale the weight initialization by square root of uh, NL. NL basically here means is the number of the input parameters coming in, fan in basically in PyTorch language. So if we divide by square root of fan n and we multiply with some gain. Now this gain square root of 2 is basically for ReLU as per the paper. And if you look at this PyTorch's timing normal method, here you see this is the standard deviation that is calculated. So fan mode is what we have to divide the weight initialization with and multiply with a gain. So gain is different for different non-linearities. So for our tan h, the gain is 5 by 3. So we'll have to multiply with 5 by 3 separately. Value is root 2. That's why we saw in the paper it as multiplying with root 2. So that is a way we can do. We these days the initialization is being done in that fashion. So basically, if we or rather divide it with mm, block size times embedding dimension, the square root of this, and multiplied with 5 divided by 3. So this could be a scaling of W1. This we can scale down to and hit in 0.5, 5 by 3. Uh, okay, so I think this might not be needed to scale this way because tan h is getting operated here. Yeah, so now, okay, sorry, I was sharing the wrong screen. So I have put manually the timing initialization formula for tan h nonlinearity here in our weight one. Let's see how it performs. So last time we were able to reach 1.77 loss here, and uh, dev loss was 2.08. Let's see if we are able to improve upon this number with the timing initialization. So I let it run again. Let's see where do we reach 2.0880, and now we are 2.0894. It's almost same. So nothing much has improved. But yeah, okay. So this would be really impactful, hopefully, in the really complex networks. And Maya, Maya Nehir, Maya Nehir, Coz, Maliz, Leo, Lope. So yeah, this is about the initialization, doing better initializations of the weights and biases. Um, as we see, as we increase the complexity going forward, we would be not manually initializing all these weights and biases. So we would be defining layers from PyTorch that we need to use, and it would internally just initialize the weights as per the dimensions given, fan in, fan out. So it would be most probably with some kind of timing initialization and based on the activations that we choose. So that's why it is not so consequential to know about this or be very careful about this these days, because we don't manually do it, and it's well taken care of with the PyTorch functions. But one thing before going ahead, uh, one thing that really helped in minimizing the in previous years, in years, let's say 5 6 years back, era when training neural network might be relatively harder with increasing complexity, there was a method that was introduced called batch normalization, which uh, would compensate to most of the uh, problems occurring here with wrong initializations. So what BatchNorm did was, if we want activations from each layer to look like unit Gaussian, why don't we just normalize them with its mean and standard deviation to be unit Gaussian? So that was the idea. It was significant, very significant in that time period, but it was also very simple. But yeah, so we'll try to implement into our network the batch norm and try to understand. So basically, what batch norm does is, I won't be going through the paper of mathematics of it. Batch norm, what it does is, if let's say there's a layer of 100 neurons, so basically you are getting a vector of 100 values, 100 float values. So that vector of 100 float values, we normalize with, we subtract mean from it, from that vector of its vector, and also we divide it by the standard deviation. And that gives us a new vector. So that would be unit Gaussian. And that's all there is to batch normalization. Now, when we implement, it might seem a bit tedious, but yeah, that's the idea behind it. So let me correct myself. There was a mistake I made in batch normalization explanation. So with batch normalization, the idea is that we don't normalize across an example or activations from all the neurons. Um, so instead, we what we do is we normalize the examples across a batch. So let's say if there are 8 examples in a batch and there are 100 neurons, and the activation shape is 8 by 100. So we take the mean and 700 deviation across axis 0, which is each 100 neurons. Each neuron will have each neuron's output of 8 different examples will have calculated its mean and standard deviation, and will let me just show it to you here what happens. So basically, let's say you have h pre-act, right? Dot shape. Its shape is 64 by 200. So there are basically 64 examples, 200 neurons. So what we'll do is we'll take a mean across 0th dimension, and let's see what is the shape now. So it becomes 1 by 200. So across the 64 examples, for each neuron, basically we calculated the mean. And similarly, we'll calculate the standard deviation. And what we'll do is h pre act minus this divided by h pre-act dot std dem equals to 0. So this is how we would calculate the new output h pre-act. So another idea is that this would force the activations at each iteration of optimization to become unit Gaussian, but it is not what we want always. What we want is the activations output to become unit Gaussian, look like unit Gaussian, uh, at least in the initial, at the first utterance, first iteration. But moving forward, as the optimizations continue, these should keep changing their shape. It should shift to left or right and expand or contract, etc. But at the initialization, it should just be unit Gaussian. So basically, what to handle that, the idea from the paper is that there is a batch normalization gain. We can multiply this with and offset by batch normalization bias. So this would be initialized with ones and this would be initialized with zeros. So at the initialization, at the first step, this would be one. So the output of this batch normalization layer will become exactly Gaussian with this calculation. And as the optimization continues with back propagation, these BN gain and BN bias will get learned, and there will be shift and scaling to done to this standardization. Let me also quickly show you, or maybe I can just paste the formula, the algorithm of mini batch, sorry, uh, batch normalization here. Yeah, you see, this is what happens is uh, you take mean across a batch, size, mini batch mean, then we take standard deviations for mini batch, we scale it with the same formula. There's an epsilon which can be used to improve this uh, and edge cases in the denominator. But this is the main thing. So here is what Bn gain is getting multiplied and Bn bias is getting offsetted with. So this is what we are trying to do here. And so to do this, we'll need to initialize these two parameters as well, Bn gain and Bn bias. So gains would be, we'll initialize them with torch dot ones, and their shape would look like um, 1 by number of hidden dimensions and 1 by n hidden. Because you see, if a size of this thing was 1 by n hidden, right? Bn gain will have across a row, for a row we'll have one numbers for gain and one number for bias, and it will keep on adding or multiplying. So yes, and this would be torch dot zeros. Yeah, so initialization done. Now we can just do this here. So yeah, so this will just turn the uh, actuations from hidden state to uniform Gaussian. And so now let's just try to train this. Let's see what happens. I'll delete this cell from here. Okay, we'll have to add these Bn gain and Bn bias to our parameters. So we'll increase the number of parameters. Now let's train it. So you see, we started here, our lowest loss was 2.03. Let's see where do we end up with this. Mm, Oh, my bad. So it only shape here. Yeah, now it should be fine. Okay, so the model was able to complete. 2.2 is the loss we were able to reach, and we'll also have to add this line of batch normalization to a dev set evaluation. Okay, so 2.09 is the loss that we are reaching to. So as of now, we were able to add the batch normalization computation into the network, and we were able to still reach to the similar loss values. We are not expecting much improvement because the network is fairly straightforward. It is not as complicated, so that batch normalization can give you good gains. But yeah, we were able to include it into our network, and the network is working as well as without it. So yeah, we were able to add correct the initialization by scaling the weights. Then we were able to add timing initialization methods. We were multiplying with the gains and dividing by the square root of n. Then we were also able to add the batch normalization to it for to control the unit Gaussian nature that it wants at the initialization at least.